discussing a statistics seminar by John Cherian. He's a fourth-year PhD here at Stanford. The problem's really interesting, okay? How can we statistically guarantee certain validity thresholds in a large language model? What that means is, in particular, large language models have stochastic outputs. So they're not the kind of models that always output the same thing. And therefore, you might be able to calibrate one output and make sure it's correct. But you have to have a certain technology in place that guarantees that the model outputs something correct every time you query it. And that's, of course, the problem here. There's a couple of fundamental issues that John shows. One is there's a couple of statistical, I don't want to call it pedantries, but clearly things that are very concerning to statisticians. For example, do you have to make an assumption of the data distribution? So if your prompt is what is the age of Aaron Rodgers, right? Do you need to understand what the distribution of Aaron Rodgers and age in the data set, in the training set that you have is? And the answer is no, because you don't want to have to understand the distribution of the data that you're querying because you don't know. Like in a large language model, which is an unsupervised learning method, you don't have a good understanding of the distribution of the data. And the high dimensionality of the data sets and feature sets is such that you just don't have a good idea. So you want to be able to relax that assumption. Another thing you want to be able to do is give confidence intervals that are subgroup independent. In other words, you want to be able to say, and there's a technical term, it's called conditional conformity, I believe, which means that you have 95% confidence interval that whatever the model says is true in any subgroup. You can also have a marginal confidence interval, that is that overall it's 95%, but you're not sure if in every subgroup. And of course, that is, again, not preferable in large language models. So these are the kinds of problems that John is tackling. And I would say that the problem set in itself is very interesting, in my opinion, because you have this problem, let's say, with full self-driving, FSD, with Tesla, right? It has very high accuracy on highways and not so high accuracy on windy speed roads like the San Jose, Santa Cruz, highway, which goes through a mountain. It's a 4-lane highway, windy and pretty speedy, and FSD doesn't do that well. So you want to be able to do well on all the subgroups. And the question is, how can you do that? So the answer is something along the lines, the technical term is quantile regression. So what you're going to do is you're going to have the model, the training data, and then split the training data into a training data and a test data. And you're going to want to make sure that whenever the prompt, what is the age of Aaron Rodgers, comes up, that you will cut out anything which is below a 95% confidence interval. There's a possibility that in the data you will have, the age, the feature age, will be at proximity to the data set Aaron Rodgers, right? It could be that's his age, but it could also be, let's say, a sentence in the age of, modern football, blah, 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 blah. So that in that sense, age would be, of course, outside of the confidence interval. It would be useless for the particular prompt. So the way you're gonna calibrate this, and there's actually a technical term, which is called calibration. The way you're going to calibrate this is by running what's called a quantile regression. and eliminating all the data points that are under a certain confidence interval. So that's the idea. Now, the problem with these approaches, the way I understand it, is there's a computational feasibility condition that has to be met. So imagine you train GPT. So you read all the available data on the internet, and you create this multi-dimensional feature space in a self-supervised way where you have lots and lots of data points, for example, names of people, such as Aaron Rodgers, and then the ages of those people. You also have the heights of those people. You have the spouses of those people. You have the professions. And so there's all this huge dimensional space. We're talking many, many dimensions here. And what this model now should do, or you want to have a statistical confidence interval where you can say that no matter what's being queried, no matter what the prompt is, and no matter also what the stochastic nature of the output is, you want to make sure that you have a certain high confidence interval that the output is correct. In other words, this is a statistical approach towards reducing hallucinations, which, as a tangent here, also explains why there are hallucinations. The reason large language models have hallucinations is because their outputs are stochastic, and there is not a guarantee in the way the model is structured that you can actually have accurate results. Now, I want to just bring one idea here to bear, which is sort of the procedural approach or the inference approach, or what O1 reflects, which is sort of self-evaluation and auto-grading. And I think I've come across a couple of attempts now. Yesterday, also in one of the seminars, the professor introduced TextGrad. The idea with auto-grading, auto-eval, TextGrad, and also this confidence interval or a conditional conformity intervals, the idea is the same. It's how can we guarantee accuracy based on stochastic predictions. So we have a model, we train a model, and it's going to output different results with the same prompts, or even with, and obviously different results with different prompts. And we want to make sure that it's accurate, not just overall, but within each subgroup. And I think there's an interesting approach to this, which is I see an iterative approach, or what people call reasoning in the industry, which is you could have a sort of TextGrad type approach where you evaluate your own answers. So you say, what's the age of Aaron Rodgers? And then the answer comes, let's say 42, I don't know. And then the model evaluates itself and grades itself. And I think that's kind of the approach also that John is using, what he calls a scoring function. But I think there could be more iterative approach, even like some reinforcement learning with verbal and scalar feedback that could improve the model's reasoning abilities and therefore also improve the accuracy. So to summarize, I am a little bit on thin ice here when it comes to the statistical seminars. There's a lot of terminology that I'm not familiar with. I do attend them for two reasons. One is, of course, I'm curious because let's not forget that AI is really built on the scaffold of statistics. So one should not neglect statistical problems by any means, to the extent that the statistics also offer solution. I am somewhat bailing out here because it is, for my taste, a little bit too technical, and I don't see the validity also for us here at Orange Capital Partners, whether it's in the fund or also here in the context of the podcast, to go too much down into the weeds. We do offer, as always, links to papers and presentations. So for people who are interested, you can go and read and evaluate yourself. I think for us, what's important is to most importantly is really to understand what are the questions. For example, in 2 days we're going to the We Robot Day with Tesla down in Burbank, and those are interesting questions. Okay, can you have conditional conformity? How do you guarantee conditional conformity? How do you make sure that the model is good everywhere? So for example, you can tell me that FST has a confidence interval of 99%, but is it in every sort of subgroup? You know, city, a curve, speed, slow, whatever. So those are interesting questions, and I think approaching them through statistics is sometimes even more interesting than approaching them through the actual application, because once you go into the weeds of the actual numbers and the formulas that underlie the models, then you understand how they work. This is really the mechanism of how it works. This would be the equivalent of understanding how DNA works in a human, and then go from there, sort of bottom up, understanding health. The same way here, you want to understand the health of a model. You really want to understand what's actually going on with the numbers, what's actually going on with the math and with the statistical models. So in this case, again, the reason we have hallucinations is because we have this stochastic prediction based on high-dimensional data space, and we want to make sure that the predictions have a certain accuracy, confidence interval in each subgroup. And we also want to make sure that we don't have to assume certain distributions of the data, which is important because we're talking about unsupervised feature spaces, unsupervised learning in determining feature spaces, so we don't know a priori, let's say, how many relationships between names and ages we have, or how many relationships between names and professions, and so on and so forth. And I think finally what I want to say also is, just in general, the statistics side of things is, of course, very important. But there's one big 800-pound gorilla which hasn't been answered in any of the seminars that I've attended so far when it's about accuracy, and that is, of course, the ground truth. That's a whole different conversation. Ground truth is, look, you can have your statistical methods fine-tuned, and that's great, but you still need some sort of ground truth. And the way, of course, statistics works is it works with large numbers, and it requires a certain minimum amount of samples to even have some sort of idea of truth. But I always bring up the example: you could potentially flood the internet with all kinds of different ages for Aaron Rodgers, and then these methods wouldn't work, right? If there's, let's say, an infinite amount of ages for Aaron Rodgers flooding the internet, then the model wouldn't be able to have any kind of accuracy prediction. It would just say, okay, there's a 50-50 chance that Aaron Rodgers is 42 years old. There's a 50-50 chance that Aaron Rodgers is whatever, or maybe not 50-50. I mean, there's a 0.001 probability that he's this age and that age and so forth. And that's of course completely useless. So how do we even know what is ground truth? To me, that's a very important question that, of course, statistics will not be able to answer, but it's still something we want to keep in the back of our minds. Thank you.